All right. Well, thank you for the invitation to speak. So I'm going to be talking about sort of two results in SYZ mirror symmetry, which are motivated by two conjectures that I want to sort of outline at the beginning of this talk. So for the purposes of this talk, I'm going to take the definition that a Calabi-Yaus manifold is a complex manifold which is scalar and has a nowhere vanishing holomorphic N0 form. So maybe this is a slightly restrictive definition of a Calabi-Yaus, but that will be the definition for this talk. So these manifolds are interesting because, at least when they're compact, Yau's solution of the Calabi conjecture says that every such manifold admits a Ricci-flat Kähler metric in every Kähler class. And so in particular, these have restricted holonomy in SUN, and so they play an important role in string theory. So throughout the talk, I'll just denote this Calabi-Yaus manifold by all of its structures. So X is the manifold, J complex structure, G is the Ricci-flat metric, omega is the holomorphic volume form, and small omega is the Kähler form. Okay, so I don't need to convince you, but of course in mirror symmetry, a fundamental role is played by special Lagrangians. So let me remind you what these are, not that I need to, but so we have this Calabi-Yaus manifold. So this definition goes back to Harvey and Lawson in the early 80s. So a submanifold of half the dimension, so real dimension n, is Lagrangian if it annihilates the symplectic form, and special Lagrangian if after rotating this holomorphic n form by a unit complex number, the imaginary part is 0 on L. So originally these were introduced because Harvey and Lawson sort of had this theory of calibrations, and this is one example of a calibration. And so in particular, these special Lagrangian submanifolds are a version of their calibrated submanifolds, and hence automatically volume minimizing in their homology class. So they're interesting from a sort of differential geometric point of view because they're volume minimizing manifolds of very high codimension. Okay, so in the mid-90s, so 1996, Strominger-Yau-Zaslow proposed a differential geometric explanation for mirror symmetry and a method for constructing mirror manifolds. So let me recall what this is. So their conjecture is that in a large complex structure limit, a Calabi-Yaus manifold should admit a fibration onto some base B, where this base comes with a possibly singular affine structure, and the fibers of this map are special Lagrangian tori. So in particular, you can think of this Calabi-Yaus manifold X as just the moduli space up to adding some singular fibers, the moduli space of one of these special Lagrangian fibers. So then how do you construct the mirror manifold? Well, they said that the mirror manifold should be constructed by just taking the dual tori to each fiber and then somehow compactifying that to get a mirror Calabi-Yaus. So this is the SYZ conjecture. So clearly one of the predictions of this SYZ conjecture is that a Calabi-Yaus manifold should admit many, many special Lagrangians. In particular, should be fibered by them. Right? So there should be lots of them. So this sort of prediction inspired a lot of work, sort of differential geometric work, looking at the existence problem for special Lagrangian submanifolds. So this has been going on over the past 25 years, and one of the main approaches to this problem is the use of the Lagrangian mean curvature flow. So the end result of all of this hard work is that actually we sort of have more sort of counterexamples or pathologies than we have positive results. So the current status of this problem is that it's unknown whether a general Calabi-Yaus admits even a single special Lagrangian submanifold. So that's obviously an issue for the SYZ program. And so for the most part, all the examples we have, so there are some sort of exceptions to this, but for the most part, all the examples that we have of special Lagrangian submanifolds are generated either by symmetry arguments or by a hyperkähler rotation trick. Okay, so this is obviously a fundamental problem for the SYZ program, but nevertheless there are sort of synthetic approaches to mirror symmetry, namely this sort of work of Kontsevich-Soyleman and the Gross-Siebert program, which seek to avoid having to actually find these SYZ fibrations and yet can still do large sort of mirror symmetry. So, okay. So this is the status of the special Lagrangian problem. So another sort of reason that they're interesting is that in the A model of mirror symmetry, these special Lagrangians play a distinguished role. So, namely, it's sort of in Kontsevich's D-brane picture for mirror symmetry, the D-branes for the A model are described by elements of the Fukaya category. So what this means is that these D-branes you can really think of sort of parametrizing particles in the physical theory Y that you obtain by compactifying type 2A string theory on X. So you can think of elements in this category as somehow describing particles. Now, not all of the particles that appear in this category are the ones that you would actually see in nature. There might be some particles that you sort of constructed by trying to glue two electrons together or something like that. Of course, those don't like to live together, so they, as soon as you let them go, they would fly off in opposite directions. And so the physical particles, the ones you might actually see in nature, are those which minimize some Lagrangian action functional. So it's sort of the typical physics, is that the actual things you see in the real world minimize some energy and hence solve some equations of motion. So if L is the Hamiltonian isotopy class of a Lagrangian in X, then its class describes a physical particle in this theory Y if it contains a special Lagrangian representative. So these are in some sense the objects that describe the physics in Y, if you like. So going back to work of Thomas and Yau and Michael Douglas, it's sort of been expected that the existence of special Lagrangians in Hamiltonian isotopy classes should be equivalent to some algebraic notion of stability. So this is a sort of long-standing expectation. And this conjecture has been sort of reformulated over the years as we learn more and more, and its current state is the following. So a Lagrangian submanifold of Maslov index 0 should be deformable to by a Hamiltonian isotopy to a special Lagrangian, for example, by mean curvature flow, if and only if the object is stable in the Fukaya category in the sense of Bridgeland. So I'm not going to say exactly which Bridgeland stability condition I'm considering here, but I think probably everybody knows which one. Yeah, so that's the next slide. Well, no, not quite the next slide. But Joyce has made some detailed conjectures also about Bridgeland stability condition and the singularity formation. And then this is what Mohammed said, which is that Bridgeland stability conditions are not known to exist in general. So really this conjecture is two conjectures, one concerning the existence of such a stability condition, and the second saying that actually this stability condition really does say something about the PDEs. Okay, so this really should be conjectures, maybe. All right, so right. So this is the sort of current version of this folklore conjecture. All right. So of course, there's a mirror to this story, which happens on the B model. So on the B model, the D-branes are described by the derived category of coherent sheaves. And then in the derived category of coherent sheaves, there's again going to be some notion of physical particles solving some equations. And the equations here, as far as I know, are only known for line bundles or maybe vector bundles with abelian gauge group, but line bundles supported on holomorphic subvarieties of X so here I'm allowing X to be a holomorphic subvariety of itself. In fact, this is encouraged. All right, so what are these equations? So this is known as the deformed Hermitian-Yang-Mills equation. So it appears sort of, so there's this work of this team of physicists who derived these equations from the Lagrangian action functional point of view. And then Lung, Yau, and Zaslow computed these equations also from mirror symmetry by looking at the mirror equation to the special Lagrangian equation. So a holomorphic line bundle over this subvariety, So this is now just some Kähler manifold. Maybe it has singularities, but let's not worry about that. Solves this deformed Hermitian-Yang-Mills equation if it admits a smooth Hermitian metric H, such that the curvature of H solves this PDE. So here it's important to point out that with F here is really an imaginary 1-1 form. And so this determinant is an imaginary volume form on V, and so it makes sense to take its imaginary part. So you see, again, this sort of appearance of the same kind of equation that we saw for the special Lagrangian, namely the imaginary part of some complex volume form is vanishing. Yeah. No. Yeah, so yeah, in a moment, yeah, so I'm going to phrase this just for any compact Kähler manifold. This question makes sense. Okay, so under mere symmetry, these so line bundles supported over all of X, admitting solutions of this equation are mapped by this sort of SYZ transform to special Lagrangian sections of the SYZ fibration. So in some sense, the solutions of this equation are giving certain special Lagrangians on the mirror, but sort of there are, of course, many that correspond to more complicated objects in the derived category coherent sheets. Okay, so the mirror then of this folklore conjecture about special Lagrangians is that line bundles should admit metrics solving this deformed Hermitian-Yang-Mills equation if and only if this class is stable in the derived category in the sense of Bridgeland. So again, this is really two conjectures, namely that there is a Bridgeland stability condition on this category, and secondly that it says something about existence of solutions to this deformed Hermitian-Yang-Mills equation. Okay, so in this talk I want to discuss two recent results from the last sort of 6 or 7 months, which are motivated by these two conjectures. So the first one concerns the existence of special Lagrangian fibrations on certain non-compact Calabi-Yaus surfaces. This is some joint work with Adam Jacob and Yushen Lin. And the second is an infinite dimensional GIT approach to this folklore conjecture and some connections with algebraic stability conditions. And this is some joint work with Yau. Okay, so let me begin with this. So log Calabi-Yau, special Lagrangians and log Calabi-Yau manifolds. So since the compact case of trying to find special Lagrangians is clearly very hard, a natural thing to try to do is to look at the non-compact case. Of course, there are, again, going to be difficulties, but if you understand the non-compactness well enough, maybe you have an extra tool to use. So a natural class of these non-compact Calabi-Yau manifolds are the Tian-Yau manifolds. So here we take some compact Kähler manifold, which admits the section of the anti-canonical bundle vanishing to order 1 on its 0 section. So in this case, we can just take 1 over this section. So that's now a section of the canonical bundle, but it has a pole on D, but it's a non-vanishing holomorphic volume form on the complement of D. Right? It has a simple pole on D. Okay, so this is a natural non-compact Calabi-Yau manifold, so X being Y minus D. So we often refer to these as log Calabi-Yau pairs. So then there's a theorem of Tian and Yau, or generalizing Yau's solution of the Calabi conjecture, which says that if you're given a log Calabi-Yau pair YD, where D is a section of this anti-canonical bundle, is a smooth divisor, assume that either Y is Fano, or that Y is fibered over a curve C with D appearing as one of the fibers of this fibration. Then the complement of D admits a complete Ricci flat metric. Okay, so these are again, so these have all the differential geometric properties of Calabi-Yau manifolds. They're complete and non-compact.
Is the symmetry known when you're multiplexing?
No, that's a big open problem. Yeah.
Sorry, can I ask?
Yeah.
So my first question is different kind of uniqueness here?
Yeah, so unique, it's sort of unique modulo the asymptotics that you put at infinity. So I think the uniqueness problem is, yeah, it's not clear. Yeah.
And one more question.
Yeah.
If you instead assume that D is like a multiple,
Yeah.
do you expect that you have something kind of close lines to not infinity anymore, but instead of one lines to
So that I'm not sure. So if you had like a, yeah. So that that I'm not sure. That I'm not sure about. Yeah. Yeah. So in the type 1 case, when y is Fano, then this Tian-Yau metric is exact. So yeah. While in the type 2 case, you have to fix some extra data, which is a Kähler class on the total space. And then there's a Tian-Yau metric for any such choice of data.
What does it mean for a vector?
So it's dd bar of a function. Yeah. Okay, so sort of a trivial observation, which is that since D is an anti-canonical section, by the adjunction formula, D is itself a Calabi-Yau manifold. So in particular, it makes sense to talk about special Lagrangians in D, where we equip D now with its Calabi-Yau metric. So then the theorem is that if L is a special Lagrangian in this compact Calabi-Yau manifold D, then the complement of D with the Tian-Yau metric admits infinitely many disjoint special Lagrangian submanifolds, which are topologically L cross S1. Yeah. Okay. Yeah. Yeah. Exactly. Yeah. So in the case when L is a torus in particular, then you get an infinitely many special Lagrangian tori. So a few. Yeah.
Let me ask that question. If you actually have a torus, it starts with an actual vibration of P by special Lagrangian.
Mm-hmm.
Upgrade that to a vibration nearby.
So in dimension 2, yes, we hope in higher dimensions, but that's yeah, we're working on it, thinking about it. Yeah.
Does this include the assumption that the normal bundle of D restricted to L is trivial?
The normal bundle of D restricted to L, no, just any special. I mean.
So this S1 is not necessarily linked in set.
Oh yeah. In fact, I'm going to write down exactly what the model is in a second. Yeah. So in fact, the normal bundle is trivial, but you don't need to assume it. It sort of follows from it being Lagrangian, exactly. Yeah. So some examples. So if D is a smooth cubic in P2, so in particular it's an elliptic curve, then of course elliptic curves admit tons of special Lagrangian S1s, right? So the complement P2 minus D admits infinitely many disjoint special Lagrangian tori. Another example, if you take a rational elliptic surface and D is a smooth elliptic fiber, then the complement of that fiber admits, again, infinitely many special Lagrangian tori. So this is the sort of type 2 case. And finally, so an example in higher dimensions, if you take this real quartic in P3, then using this anti-holomorphic involution, Robert Bryant proved the existence of a special Lagrangian torus in D. So then the complement of D admits infinitely many disjoint special Lagrangian tori. So let me explain a little bit how this goes. So the first step is to use the model geometry of the Tian-Yau metrics at infinity to carefully construct some approximate special Lagrangians in X. So let me just explain the model geometry in the type 1 case. So in this case, we have here's the model. So we have a Calabi-Yau manifold projective. Its dimension is m-1, and L over D is an ample line bundle. Then the Calabi-Yau, so we can take a metric on L, whose curvature form is the unique Calabi-Yau metric in the first Chern class of L. So if you take a local coordinate on the total space of L, then we can look at this set, which is all the sections which have norm bigger than 0 and less than 1. And we can put a holomorphic volume form on this set. And here's the Calabi-Yau metric. So this you can just compute as Calabi-Yau, and it's complete near 0. So this is somehow the model geometry for the type 1 case. So where are the special Lagrangians? Well, it's not hard to guess what you should do. If you have a special Lagrangian in D, then you just take the circle bundle over this special Lagrangian, and you can check that that's special Lagrangian in the total space here. So this is the sort of model geometry in the type 1 case. So you then have to lift this to the actual manifold and then deform it so that it stays Lagrangian with respect to the actual Calabi-Yaus metric. And then once you do that, then you run the mean curvature flow and you can prove smooth convergence to at least an immersed special Lagrangian. Oh, because the original model was M cross S1, right? Because this is just an S1 in the total space of the bundle. Yeah, right. But it's the line bundle is trivial restricted to D because it's a Lagrangian submanifold, and omega is the.
No, L is Lagrangian.
Yeah. Yeah. Okay, so then you can prove that you run the mean curvature flow and you prove a bunch of estimates and you prove that the flow converges. And the main difficulty here is that in the type 1 case, actually these Lagrangians it's kind of like a stability theorem for the Lagrangian mean curvature flow, except that these Lagrangian manifolds in some sense degenerate at infinity, because if you just look at the model, as you sort of move out towards infinity, these Lagrangians are like collapsing S1 bundles over a Lagrangian which is expanding in the base. So in some sense, the geometry improves as you go to infinity, but it also degenerates. So there's some, you have to show that the improvement in the geometry actually beats the degeneration when you run the mean curvature flow. Okay, so anyways, you can do that. Right, so it's just saying what I just said. Okay. So in dimension 2, we can actually do better. Namely, we can prove that at least when y is a del Pezzo surface or a rational elliptic surface with a smooth divisor in the anticanonical bundle, then for any choice of closed loop in D, x being y minus d with the Tian-Yau metric emits a special Lagrangian torus vibration onto the R2. Okay, so this is, of course, sort of confirming this SYZ conjecture, the existence of this vibration in this case. Auroux also made some conjectures about this situation, and in particular that the base should be R2. And he also made some conjectures about what the form of the vibration should be near infinity, which are also confirmed by the proof. And then I should point out that Lung and Yau actually also made some conjectures about the existence of twin special Lagrangian vibrations. And you see that here we get a ton of special Lagrangian vibrations because essentially for any choice of special Lagrangian in the torus at infinity, you get a vibration. So there are, in fact, sort of many distinct special Lagrangian vibrations, and that was predicted by Lung and Yau.
So are those fibers are smooth, or are they singular fibers?
No, there will be singular fibers, yeah. And I can say what they are in some cases. So if y is P2, so then D is a cubic, then the singular fibers are 3 nodal spheres. So Katyra type I1. So this was conjectured by Auroux. So he conjectured the existence of this vibration with 3 nodal spheres. And if y is a rational elliptic surface, then at least for generic choices of data, for example, for generic choices of the Kähler data and for generic choices of elliptic curve appearing in the vibration, then there are 12 nodal singular fibers. So this is also conjectured by Denis. Okay. So how do we do this? Well, we've already constructed a bunch of disjoint special Lagrangian tori using the mean curvature flow. So now you can hyperkähler rotate so that these special Lagrangians become holomorphic. And then you can apply the sort of deformation and compactness theory for holomorphic curves. So there's some issues here because, of course, we're working in a non-compact case. So one needs to prove some results that show that this deformation theory and compactness theory really works. And then the hard part is or the sort of key part is to rule out the accumulation of singular holomorphic curves. So essentially what you have is you have a smooth, so by the mean curvature flow, we have a smooth special Lagrangian. It deforms to a family. So you can show that the deformations don't intersect one another, so you get a local vibration. And then what you want to do is show that there's no sort of boundary that forms that prevents you from deforming past some point. So to do that, you just need to show that you can't have singular holomorphic curves which accumulate at other singular holomorphic curves. So that we can do. But the proof sort of begs the question, well, what is this hyperkähler rotation of the Tian-Yau manifolds? So we used the hyperkähler rotation. So what is that manifold? And we can identify it. So if Y is a del Pezzo surface or a rational elliptic surface with this smooth divisor, self-intersection D, then we have this special Lagrangian torus vibration. So if after hyperkähler rotation, this becomes a holomorphic vibration, genus 1 vibration over C, which can be compactified to a rational elliptic surface by adding a singular fiber at infinity of type ID. Okay. So, so a few remarks about this theorem. So at least at the homological level, mirror symmetry between del Pezzo surfaces of degree D and rational elliptic surfaces with an ID fiber is pretty well established. So for example, Oru, Katsarkov, Orlov proved one direction of Koncevich's conjecture by showing the equivalence of the derived category of coherent sheaves and the Fukaya-Seidel category of this Landau-Ginzburg model. So Dorr and Thompson also showed the mirror correspondence at a lattice theoretic level. And Luntz and Tsiolkovsky showed the correspondence at the level of Hodge numbers following this proposal of Katsarkov, Koncevich, and Pantev. Okay, so this fits pretty well into this picture, but it's sort of slightly mysterious because it's unclear whether this hyperkähler rotation actually achieves the correct SYZ mirror because we don't know whether the complex structure is the right one. But in some cases, so for example when Y is P2, then the mirror rational elliptic surface with 3 I1s and an I9 is rigid. So it has to be, whatever we get, there's only one of them, it has to be the right mirror. So this is maybe slightly surprising since I don't think it's expected that hyperkähler rotation produces the mirror in general. But there's some evidence that in fact for these models, this hyperkähler rotation really does produce the SYZ mirror. Yeah. Right.
You know what the complex structure is on the thing you produce.
So it's just the hyperkähler rotation. Yeah, yeah.
So you could ask, is it a homological mirror?
Right. So that for sure, because the categories I think don't. So on the other, so at least the direction that's going, like the homological level, I think maybe doesn't see the instanton corrections on the symplectic side, right?
It is only one direction of mirror symmetry now.
Mm-hmm.
So you don't know the other direction.
Right. Yeah. Exactly. Yeah. 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 So right. So the point is that we get the sort of right manifold, but maybe the wrong complex structure. So that we're not sure about. Because you see this hyperkähler rotation is sort of not a Fourier-Mukai transform in any, yeah. Anyways. All right, so in work in progress, we can extend this to some certain singular settings. So if you take a rational elliptic surface with an ID singular fiber, then this has a complete Calabi-Yaus metric constructed by Hein. And then what we prove is that the complement of this ID fiber emits a special Lagrangian torus vibration with base H2, and you can again identify the hyperkähler rotation. So this is kind of a relief if you think about the SYZ picture, because if you started with a Fano with a degree D divisor, then by this hyperkähler rotation we get exactly one of these Y minus IDs. But by the SYZ picture, it should have a dual special Lagrangian torus vibration, right? But in the a priori, it's not clear where that special Lagrangian torus vibration is, and here we produce one of them, or we produce the special Lagrangian torus vibration. Okay, so we have to understand what this hyperkähler rotation is really doing, and we have this nice work of Gross-Hacking and Kiel, which we can compare our results with. So. Okay, so that's the first thing that I wanted to talk about. So on to this nonlinear PD instability in mirror symmetry. So let me recall this folklore conjecture. So this folklore conjecture is predicting the sort of equivalence between stability in the sense of Bridgeland and the existence of PDEs on the complex and symplectic sides. Okay, so since we don't know whether Bridgeland stability conditions exist, working on this conjecture, yeah. Yeah. Mm-hmm. Mm-hmm.
Do you understand how the moduli of tensors correspond to rotations?
No. Yeah. We other than these two cases, we almost know nothing about the singular fibers. Yeah. Yeah. Okay. So since we don't know whether these Bridgeland stability conditions really exist, working on a conjecture proving the existence between solutions of PDEs and some unknown stability condition might seem hopeless, and I wouldn't argue with you. But what we can instead do is forget about Bridgeland stability for the time being and just try to understand the sort of relationship between these two PDEs and algebraic geometry. And then if we can understand this, we can try to fit this back into the Bridgeland stability, the sort of conjectural Bridgeland stability picture. Okay, so how do you do this? Well, there's a fundamental idea which goes back to T.M. Bott and Donaldson, which is if you're in this situation, you should try to view your PDE as the zero of some infinite dimensional moment map, right? And then if you can do that, then you can try to look for some infinite dimensional GIT framework in which your equation should correspond to some stability condition. Okay, so that's what we're going to try to do. But let me first try to explain this PDE a little bit. So fix a Kähler manifold now, so it doesn't matter whether it's projective, Calabi-Yaus, and some class in H11 XR, which you should think of as the first Chern class of the line bundle, but we consider R classes because if you're interested in B fields, then this is the natural setting. So then the question is, when can we find a representative of this cohomology class which solves this PDE, where this e to the I zeta is some fixed point in S1? So where does this point come from? Well, if this holds, then it should hold after you integrate, but the integration of this is some cohomological thing. So this e to the I zeta is determined by this integral. So there's a caveat here, which is that this integral could very well be 0. Okay, so I'm going to assume that that's not the case. But this will sort of reappear later, trying to understand when that happens. Okay, so we have this integral, which lies in this ray. And this is equivalent to the deformed Hermitian-Yang-Mills equation by just taking the minus the first Chern class of the line bundle to be your cohomology class. Okay. So we can rewrite this equation in terms of a relative endomorphism of the tangent bundle in the following way. So you just raise an index of this form using the Kähler metric. This is a Hermitian endomorphism, so it has eigenvalues. And you can just sum the arctans of these eigenvalues. So this is an operator. Takes in forms and spits out real numbers. So then the deformed Hermitian-Yang-Mills equation is that this operator is a constant. And that constant, so this is another sort of subtle but important point, that this constant is between minus n pi over 2 and n pi over 2. But it's only determined mod 2 pi by cohomology. So a priori, if you can solve the equation, you already get more information than you were getting out of cohomology. Okay. So a little bit of context. So recall that a graph in Cn is special Lagrangian if and only if it satisfies this equation, where these lambda i's are the eigenvalues of the Hessian of f. So this operator is sort of pretty well, or much studied anyways, in the real PDE literature. So this deformed Hermitian-Yang-Mills equation is therefore a natural, complex, and global in the sense that it's over a compact complex manifold version of this graphical special Lagrangian equation. Okay, so with Jacob and Yau, we studied, so gave some necessary and sufficient analytic conditions for the existence of solutions when this right-hand side is fairly large. But to connect with the conjecture, you really don't, I mean, these analytic conditions are not so useful, so what you want are algebraic conditions. So let me explain how this is done. So fix some representative of our cohomology class. then by the DD-bar lemma, any other element of this class is just related to this fixed representative by the Hessian of a smooth function, smooth real-valued function. So then, based on ideas of Thomas and Solomon in symplectic geometry, we're led to consider this space of functions, so that this operator differs from theta hat by less than pi over 2. So this is shorthand for this form. And this theta hat is just any element of this range which agrees with this cohomological constant, mod 2 pi. Okay, so if there's a solution of the deformed Hermitian-Yang-Mills equation, then it has to lie in one of these spaces for some theta hat, right, just by definition. Okay, so there's a bunch of these spaces. There's sort of one for every lift of zeta mod 2 pi to this interval. So by the maximum principle, there's at most one value in here for which this space is non-empty. So that's good. So if H is empty for all theta hats, then there can't be a solution. That's kind of trivial. And the key point is that this space H can be made into an infinite dimensional Riemannian manifold. So how do you do that? Well, this space H is an open subset of this space of smooth functions. So it's at any smooth function, its tangent space is just a copy of the vector space. And so we just need to just say how to take an inner product of two smooth functions, and you do it using this inner product. So the key point here is that the definition of H is exactly the one that makes this a volume form. So this is a non-degenerate L2 inner product. Okay, so from now on, I'm going to assume that we're in this large phase case. Okay, so associated to this Riemannian structure, there's a notion of geodesics. So once you have a Riemannian structure, you can measure lengths of curves. And then, of course, you can look for shortest curves. So I'm going to discuss these, but let me first say what the upshot is. So we can consider this one form on H. So given an element of the tangent space, you just take this integral. So the point here is that this volume form vanishes at solutions of the deformed Hermitian-Yang-Mills equation. So this one form has zeros only when you're at solutions of the equation you're trying to solve. So in fact, this is just the Kempf-Ness functional, or the derivative of the Kempf-Ness functional for this GIT problem. So this functional integrates to a perfectly well-defined functional. So this one form is d of a function on the space H. So by construction, it has critical points at solutions of the equations that we're interested in. And then the second key point, which comes from the GIT package, is that this function j is convex, at least along smooth geodesics in the space H. Okay, so now we've sort of reduced the problem to the following sort of formal problem. To solve this deformed Hermitian-Yang-Mills equation, we just need to show that this convex function has a critical point, right? It's GIT. So there are two pictures. So either we could be in this nice picture. So there's our solution of deformed Hermitian-Yang-Mills equation. Or we could be in this sort of bad picture. So in this case, there is no solution. So these two pictures are distinguished by the slope of j near the boundary. So for this nice picture, the slope is positive in all directions. And for this bad picture, the slope is negative in one direction. So to try to make this picture rigorous and to connect with the folklore conjecture, there are sort of three steps that we have to do. So the first is to establish the existence of sufficiently regular geodesics in this space H. The second is to understand, in some sense, some points on the boundary of H and their connection with algebraic geometry. And third, we have to produce these geodesics going to the boundary of H and evaluate the limit slope of J in terms of some algebraic invariance. Okay, so let me just say what the geodesic equation is quickly. So it's easiest to write the geodesic equation on this product complex manifold. So this is an annulus in C cross X. And then we have this DD bar, which is the complex Hessian on this big manifold. So this is the PDE. So it looks a lot like the deformed Hermitian-Yang-Mills equation in dimensions n+1, but now this Kähler metric in the background is degenerate, so it's not a Kähler metric anymore. And this is really the reason that this geodesic problem is hard, is that this equation is degenerate, elliptic, and fully nonlinear. So in general, there's sort of no regularity theory for this. Certainly no smooth solutions in general. So a real analog of this equation was studied in a domain by many people. And the upshot of all of this is that there are continuous geodesics. So it's basically some application of a sort of Perron method using ideas of Harvey and Lawson. But to do this GIT, this sort of continuous regularity is not enough. So you need better results or better regularity theory. And the difficulty here is that in general, you don't expect to have any regularity for fully nonlinear degenerate elliptic equations. So, but with, so the sort of main technical result in our paper with Yau is that at least in this large angle case, you can solve this geodesic equation with C1 alpha solutions. And in fact, it's sort of almost C2 for any boundary data. So in particular, this regularity is enough to make sense of this picture. So this functional J can be defined, and it is convex along geodesics. Okay, so that's the main PDE input. So now we sort of move on to step 2, which is to construct curves going to in H going to the boundary. So this is based on the choice of the following data. So you take some filtration of the structure sheaf of your manifold by a nested family of coherent ideal sheaves. And then you can sort of produce by hand a curve in H which becomes singular as t goes to 0. So it's smooth for every t not equal to 0. And when t equals 0, it becomes singular. And the singularities are exactly modeled on this filtration. So I won't write down the formula. I don't know how instructive it is anyways. So now the picture is the following. We have this curve which goes to the boundary of H. It develops singularities. And now we can just start, we want to sort of approximate this curve with geodesics. So we just start connecting points on the curve with geodesics. So then we can evaluate the limit slope. And once we do that, we'll have some obstructions. So the simplest case of this construction is when you just take one ideal sheaf, and that ideal sheaf is the ideal sheaf of a subvariety. And now let me assume for aesthetic purposes that this class is really the first Chern class of a line bundle. So then we can introduce these two numbers, zv of L and zx of L. So you see they're almost exactly the same, except one of these intersection numbers is computed on V, where one is computed on X. So then here's a sort of summary of the theorem. So it turns out in this large phase case that zx of L always sits in this quadrant. So then there are essentially three cases. So there's the region in the upper half plane to the left of this vector. And if zv of L sits in this region, then L is not obstructed. So this is sort of what you would expect for a stable line bundle that admits solutions of deformed Hermitian-Yang-Mills. If it sits to the right of the vector, but in the upper half plane, then L is obstructed. So there's no solution of deformed Hermitian-Yang-Mills. And if it ever sits in the lower half plane, then in fact this space H that we began with is empty. So it's even worse. You're even more obstructed.
Sorry,
Yeah.
I came in a bit late. So your L is what kind of line bundle?
Any holomorphic line bundle on X.
So I mean, the deformation theory of such a line bundle is the same as the deformation theory of structure.
The deformation theory of such a line bundle is the same as the okay.
So, I mean, either your structure sheaf is obstructed or it's not. It's not.
Well, but this is an invariant that depends on this first Chern class of L, right?
But, I mean, you make this statement about you have this or that, depending on whether or not it's obstructed.
Yeah. But these numbers depend on the Chern class of L, right? Obstructed, I mean admits a solution of the PDE. It cannot admit a solution of the PDE. Yeah. So it's like a GIT obstruction to the existence of a zero of the moment map or something. Yeah. Okay, so let me explain the connection with Bridgeland stability. So these obstructions that we get, so I should say that these are just sort of a special subclass of the obstructions that we get, but that may be the simplest to understand. So these obstructions turn out to be pretty closely related with this conjectural Bridgeland stability condition with respect to this Douglas-Bridgeland central charge. So let me explain how. Well, there's first a caveat, which is that you would like to think of the obstructions that we're getting from this point of view as arising from surjections of L onto L tensor skyscraper sheaf supported on V. But our invariant doesn't agree with this Douglas-Bridgeland central charge. So everything here has to be taken modulo this statement. So to explain how this stability type structures appear, I really need to explain how to define this slicing angle that appears in the definition of a Bridgeland stability condition. So this slicing angle is some number in R which agrees with the phase of ZV mod 2 pi. Okay, so how do you do that? Well, you consider this path. So you basically interpolate with the large radius limit. So you consider this path where t goes from plus infinity to 1. So if this path lies in C star, then it has a well-defined winding angle, and we can define the slicing angle to be this winding angle minus this dimensional factor. So when is this well-defined? Well, if dimension of V is 1 or 2, then this path always lies in C star automatically. So 1, it's trivial. 2, it's a consequence of the Hodge index theorem. But in dimension 3, this path can go through the origin. So it's easy to construct examples where that happens. So it turns out that if you can, so in this case, this slicing angle will not be defined, but that's actually not such a problem because in the Bridgeland stability framework, you only assign phases to semi-stable objects, right? Which somehow you should think of as having some sort of solution of the PDE. So we can prove that if, at least in dimension 3, if you have a solution of this deformed Hermitian-Yang-Mills equation, then there's a Chern number inequality which guarantees that this path does not pass through the origin. So we sort of expect to have inequalities in dimension n involving all the Chern numbers up to the highest dimension, but they sort of get harder and harder to prove. But in any event, with this result, at least for the sort of semi-stable objects, we can define this slicing angle for any subvariety in dimension 3, including x itself. So then you can rephrase our results in the following way. So if L over this threefold has a solution of the deformed Hermitian-Yang-Mills equation, then first the Chern number inequality has to hold, and the slicing angle is in this quadrant, pi over 2 pi. This number ZV of L lies in the upper half plane for every V contained in X, and you have this inequality of slopes. So this really looks like a Bridgeland stability kind of structure in the sense that this is saying it lies in the upper half plane. This is saying that these L tensor OV are in the heart for all V, and that you have stability. Okay. All right. So at least you see the sort of Bridgeland stability framework coming out of the PDE. So. Okay, so what can we say about the mirror manifold? Well, using SYZ mirror symmetry, at least in the case where it works on the nose, we can apply our results to the existence problem for special Lagrangians. So consider a toric Fano manifold. It's a case where SYZ sort of works. So then the mirror of this SYZ, the SYZ mirror is this Landau-Ginzburg model YW. So Y you can think of as an open Calabi-Yaus manifold, which is a special Lagrangian fibration over the moment polytope of our toric Fano manifold. So then a holomorphic line bundle over this manifold with a metric in this space H becomes an almost calibrated Lagrangian section of the mirror SYZ fibration. And under this correspondence, our GIT picture becomes a sort of GIT picture which is due to Thomas and Solomon. And crucially, the sort of key ingredient is that our geodesics become geodesics in the mirror, in the space of Lagrangians. So our degenerations in geodesics become degenerations in geodesics in the space of Lagrangians on the mirror. And you get invariants from this picture which allow you to obstruct the existence of special Lagrangians. So let me just draw an example because that's the best I can do. So consider just P1. It's the easiest case to draw. So the moment polytope of P1 is just an interval. And let me go to the sort of universal cover of the of the cylinder over 0, 2, which is the Landau-Ginzburg model. So assume we're taking a degeneration which corresponds to this ideal in OP1, and let's consider the line bundle O minus K. So then from our construction, what you get is a family of Lagrangians in this mirror, which drawn in the total space undergo a degeneration that looks like the following. So we start with some line bundle, and you start turning on this degeneration, which corresponds to this parameter t. And as t goes to 0, these Lagrangians do something like this. And in the limit, they break. They split off a factor here, and they split off a factor here. So they undergo a sort of degeneration. And associated to this degeneration, there's a numerical invariant which is supposed to obstruct, which does obstruct the existence of special Lagrangians in the Hamiltonian isotopy class of this L, suitably interpreted. So, okay, so you can sort of imagine, at least at a sort of intuitive level, that what's happening here is this Lagrangian is bubbling off torus fibers. But these torus fibers don't live in the manifold, so that's not so easy to understand. So then you walk across the hall and ask Paul Seidel how to think about this. And the point is that you should think about this by that these torus fibers that are bubbling off should be mapping, sort of regarded as certain mapping cones in the Fukaya category. So in particular, for any toric manifold, we can produce lots of obstructions, algebraic obstructions to the existence of special Lagrangian sections in these LG models. The caveat is that at the moment we only know how to express these invariants in terms of the complex geometry on the mirror. So having a purely symplectic version of this or formulation of this would be very nice in order to understand how it connects with the Bridgeland stability point of view on the Landau-Ginzburg model. So I'll stop there. Thanks. So that might just be a consequence of the fact that I was only considering P1 here, but no, yeah, just P1, yeah. But somehow, because all of these degenerations have to be supported over the boundary of the polytope, and even in an arbitrary dimension, because they come from the sort of map only works when you consider toric degenerations, which of course correspond to various facets of the polytope. So in general, these degenerations are going to take your Lagrangian and deform it, and in the end it's going to split, and how it splits depends on the particular ideal you chose or family of ideals you chose. So yeah, so I actually don't know well here I'm considering sort of the B model on the toric Fano mapping to the A model on the Landau-Ginzburg model. So I think going the other way, I don't know. Then maybe it would be more related to special Lagrangians in the complement of D. But.
What is the final statement about this?
About this? Yeah, so the final statement is take the mirror of one of these guys and express it as a holomorphic line bundle. But I think that what it should be is that, so you give me a, right. So the statement is that you give me a special Lagrangian, or a Lagrangian section of the Landau-Ginzburg model, the SYZ fibration of the Landau-Ginzburg model. A section? Oh, I mean, if it's mirror to a toric Fano, then it exists by the construction, basically. You can just sort of, yeah. So you take one of those sections, you interpret it as an element of the Fukaya category, which is something that I don't know how to do and surely involves the superpotential. And so then associated to any sort of, okay, so now I have to be a little careful because I don't know exactly what the data is, but essentially I think the picture should be associated to any piecewise linear function on the polytope there is an invariant, which should be related to Bridgeland stability, and which, if it's sort of has the wrong sign, tells you that there's no special Lagrangian representative in the Hamiltonian isotopy class of that. Yeah. Yeah. Yeah, because it's just mirror to the statement that we made about holomorphic line bundles. Yeah, in this case, you can just sort of write formulas down. Yeah. Yeah, exactly. Yeah, so basically in this toric-Fano case, you can do like semi-flat mirror symmetry. So it sort of works. But, yeah. Yeah. So that's really more my ignorance of how to understanding the Fukaya category on the toric manifold. I think more. It should be, yeah. It should be, yeah. Yeah. It's purely in terms of intersection numbers. So somehow it's formulated on the Grothendieck group of dB coax. No. Yeah, it's purely algebraic. Yeah. So there should be a mirror statement for the Fukaya category.